All right, this was the second half of the continuity assignment. I'm starting problem 19 and then moving on up. The first, I think, 6 questions wanted you to examine whether or not there were discontinuities, locate those discontinuities, and then tell whether those discontinuities were removable or non-removable. So basically, if it's a removable discontinuity, it's removable. And if it's a jump discontinuity or infinite discontinuity, it's not. So with 19 piecewise function, the line is always continuous. These are both lines. So each half of the function is going to be fully continuous. But what about the breakpoint? And so we test the breakpoint, we plug a 2 in to each function. The left function is coming to a height of 1, the right function is coming to a height of 2. That creates the jump discontinuity. So for part A, I would say there's a jump discontinuity at x equals 2. And they just gave the location x equals 2. But a full answer would describe that, the type of discontinuity. Jump discontinuities are not removable because the left limit and the right limit are not equal. And to be able to fix a discontinuity, the limit has to exist, which only happens at removable discontinuities. Number 20, similar piecewise function, 2 lines, right? 3 minus x is a line with a slope of -1, x over 2 is a line with a slope of 1/2. But this time when I plug the 2's in, the breakpoint here is at 2, I get a common height. Both lines are converging on a height of 1. Now my function doesn't allow me to use either of those functions, and they actually tell me where they want the y value to be. They say at 2, they want the y value to be at 2. And so you can see it creates a removable discontinuity, or hole, right? A hole is what causes a removable discontinuity at x equals 2. So that's what I would say for part A. There is a removable discontinuity at x equals 2. And part B says, is it removable or non-removable? Yeah, a removable discontinuity by definition is removable. What were the reasons for my answer? Well, because if I change this value right here, if I say instead of having the function have a height of 2 when x is equal to 2, let it have a height of 1, well, boom, you just plugged that discontinuity, didn't you? And so that's number 20. 21, very similar piecewise function, except this time I have a rational function coming in from the left and a cubic function from the right. And so this is what the graph would look like. And we've got a real problem at 1, don't we? We've got the 1 just happens to be the location of the vertical asymptote for the rational function. So the limit as we approach 1 from the left is -infinity, which isn't a real number. So the limit really doesn't exist there. And the right limit is 4 coming in from the right. But with the infinite discontinuity, there's no way we can fix this situation, so it is not removable. Number 22, this time we have a parabola in it's good everywhere except for 1 point, except for at x equals -1, where they define us at 2. So here's where they tell us they want the height to be when x is equal to -1. So it does create a removable discontinuity. There's a removable discontinuity at x equals -1. But if I just change this to 0, I just redefine the piecewise function to have a value of 0 when x is equal to -1, that fixes that up, right? It fills in that discontinuity. And that's 22. 23 was a picture which they gave you, and apparently I don't have it. I'm going to grab it for you really quick. going to have it later on in this document, but we might as well look at it at the same time. So let me pause, and I will see you here in just a second. All right, so back again. Here's that graph that was referring to problem 23, and where are the discontinuities? Well, this is only defined from -1 to 2, it looks like, and it's continuous until we get to 0. There's a removable discontinuity at 0, which could be fixed. There is a jump discontinuity at x equals 1, which cannot be fixed. And that's it. So it looks like that's what's going on. So as the part A says, there are 2 discontinuities at x equals 0 and x equals 1. And then the removable discontinuity at x equals 0, the jump discontinuity at x equals 1 is not removable because the one-sided limits are not equal. 24 was this guy right here, and it looks like we start at -1. We're fine until we get to, it looks like 1. We have a jump discontinuity. At x equals 2, we have a removable discontinuity. And at x, well, and then it's done at x equals 3, isn't it? So over its domain, over its defined interval domain of -1 to 3, there are 2 discontinuities at x equals 1 and x equals 2. And the first discontinuity is a jump discontinuity, which is not removable. The second discontinuity is a removable discontinuity, which could be fixed by redefining the height of the function to be equal to 1 at x equals 2. All right, 25 through 30 got into a different kind of question. They wanted us to write extended functions. So you have these answers in your course pack, and the work is included, which I think is nice. But this is that process that we went over in a couple of examples yesterday, and I want to work a couple of these out just to make sure that that you guys are down with how this works. Okay, so the answers for 25, 26, 27, 28, 29, 30 are here, but I'll be working some of those out, going through that process just to make sure that you get it. And you should have these answers all on your course pack with all the factorization, which is kind of nice. All right, now the next set of problems, 31 through 34, gave you some functions that they wanted you to explain how you knew they were continuous based on these properties of continuous functions that we talked about on Tuesday, which are in your course pack. Okay, basically, if you have f and g, which are continuous functions, this just says you can add them, subtract them, multiply them, divide them, or even take compositions of these functions, and you will get new, also continuous functions. So like at 31, I know the square root function is continuous. I know the line, any linear function, any polynomial is continuous, so x plus 2 is continuous. So when I take the composition of g of f by putting the line into the root function, it definitely is going to create a new continuous function. Okay. As far as the domain goes, the original function could not have any values less than -2 because of the square root, and that domain has to follow that function into this new composite function. We still have a domain which can't have any values less than -2. Okay. In this case, we can't even have -2 anymore because it's in the denominator now. That becomes an issue. When we divided 1 by our new function, we can't have zeros in the denominator. 32, x squared is a polynomial, so it's continuous. The cube root function is continuous. The line 4 minus x is continuous. These are all continuous functions. So when I take the composition of a cubic and a linear function for the second part of this, it's continuous. When I take the quadratic and add it to that, that's adding two continuous functions of continuous. All four or all three of those functions, linear, quadratic, and cubic, all have degree ranges of domains of all real numbers. So the new domain will still be all real numbers. And we're using these properties on this problem. We added continuous functions, and we certainly took the composition of continuous functions. So those are kind of the properties that we used to make that statement. Number 33, the absolute value function is a continuous function. We already talked about how all polynomials are continuous, including quadratics. And so if I take the composition of functions by putting a quadratic into an absolute value function, it will be continuous. And once again, we're using our composition part of that relationship to come up with that statement. By the way, absolute value functions and parabolas both have domains of all real numbers, and so you can see that that domain followed those functions to this new function. The last one is a piecewise function, so it's really just this rational function here, which is continuous everywhere except where it has 0 in the denominator. And so there is a hole at x equals 1, but if you factor that, x plus 1, x minus 1 on the top, and cancel the x minus 1s, really this function just turns into x plus 1. So if I put this 1 in here, I realize that the height of the hole, 1 plus 1, is 2. So look what they did. They plugged that single hole, and they made the function continuous. So its domain would be all real numbers now, and it would be fixed all the way through to achieve that. So that's what was going on with that set of problems. This next set of problems was a really good one. And these are just possible answers, okay? Just possible answers. But I'll tell you what you should have been looking for in your graph. 35 said that the limit as we approach 3 exists. I'm sorry, the limit does not exist, but f of 3 exists. So you had to have a jump discontinuity at 3. Okay, you couldn't have a hole because then the limit would exist, and this said the limit does not exist. So you had to have, and it couldn't be infinite because f of 3 had to exist. So you had to have a jump discontinuity. You could have plugged either of these values with that hole, or you could have left both of those open and then just put a random point somewhere else. So, another answer could have been like this. This is this part. This part goes like this. There's that jump, and then, we define it right there. So that would have been fine. There's a lot of different ways you could have done that, but you had to have a jump discontinuity at x equals 3, and you had to have a point, whether it was connected to one of your functions or just another point somewhere there, because it did say f of 3 exists. Number 36 says f of negative 2 exists. So once again, at negative 2, we're going to have a point. This one gets a little more specific. It says the right limit as f of x approaches, as x approaches negative 2, is equal to the function's value at 2. So you had to have this part of your graph end at the function's value at that point. You had to have this closed hole on the right part of the graph. Now, at the same time, the function overall as x approaches negative 2 does not exist. So once again, it can't be an infinite discontinuity because we already said that there's a value there. But it can't be a hole because it says the limit does not exist. And so you need another jump discontinuity on this problem. There had to be a jump discontinuity at x equals 2. But this one was a little bit more limited because, as opposed to 35, where you could have put the point anywhere in here, on 36, it had to be connected to the right part of the graph. So just another example, you could have had, this function come all the way over and end at a defined point, so the limit had to equal the function's value, but then you had to have some kind of a jump. and then, something like that. So as long as you had those two conditions, you were in good shape. Now, number 37 said f of 4 exists. So once again, I'm going to have a point for f of 4 somewhere in here. Okay. But this time it said the limit exists. So that's very cool. That means that both sides of the graph are going to be approaching the same height, right? But it's not continuous. So the only way that could happen is at a removable discontinuity. And so what you had to have here was your two sides of the graph converging at the same point, and then a hole, but then the function had to have a value somewhere else. Okay, so another example of this one would have been maybe like this, come into 4 from both sides, we're coming to the same place. The limit existed, unlike 35 and 36. However, there was no continuity, so I had to define that place somewhere else. So that's what that would have looked like. You're basically using these clues to determine which of the 4 possible situations could occur. And the 4 situations are continuity, removable discontinuity, jump discontinuity, or infinite discontinuity. Now 38 said that the function is continuous everywhere except for x equals 1. So I know something's happening at x equals 1 here. The function has a non-removable discontinuity there. Well, an infinite discontinuity is certainly an example of a non-removable discontinuity. That's one way that you could handle this. But a jump discontinuity is also non-removable, so I suppose you could have also had a jump discontinuity come in. Something like that would have worked also. It doesn't say whether it's defined at 1 or not, so I guess you could have left it like that. But you probably could have also, filled in one of those holes for a defined value. I think you had some flexibility there. So that's how you did those problems. These are just possible examples, but as long as you got those conditions, those parameters right, you were in good shape. 39 was really just an algebra problem. It wasn't really a limit problem. So if you were kind of thrown off by it, it didn't really fit in with the rest of it, but I thought it was a really good algebra problem. It told us, it asked us if any number was exactly 1 less than its 4th power, basically. Is any number exactly 1 less than its 4th power? So it's asking, is any x, right? Is any x exactly 1 less than that value's 4th power? And so I just set up an equation here, and I'm like, wow, I don't know how to solve that. So I used the, I guess I could have set it equal to 0 and then graphed it, but what I did is I graphed each half of this, so the line y equals x and the equation x to the 4th minus 1, so this is what the graph would have looked like, and then I just let the calculator do its work, and these are the answers that came up. So those two numbers right there are exactly 1 less than if you would have raised that same value to the 4th power. So interesting algebra problem, but don't worry about it. Now this one was a really important limits problem, so I'll let you look at the answer here. Of course, you already have it in the course pack, but I'm gonna end up going over this one. So I'm gonna do some of those extended function problems for you, and then I'll do 41 before the end of this video. The last problem before we do that was 45, which was a good limit problem, and it had lots of stuff going on. This function is a pretty scary looking function. It's a combination of a rational function and an exponential function. Probably the first thing you do with it is you graph it, and you end up with something that looks like this right here. And it asks what the domain is, and you're like, okay, looks like everything's good up to -1. It looks like everything's good back to 0. Now, what's happening between -1 and 0? That is where things get a little freaky. This is the full graph that you would get on your calculator if you just did it right off the bat. And so what's happening in this area right here just looks like pure chaos. looks kind of like almost one of those oscillating discontinuities that we know about, we don't really do much with. So we'll talk more about that. But what's happening here is the function is like blinking in and out of existence. Most of the time, it does not exist because of undefined values. But in certain cases, it does. And so it's too hard to determine where it does and where it doesn't. So what we're going to do is we're just going to say that the function is defined from negative infinity to -1, and then between -1 and 0 it disappears, and then from 0 to infinity it's good. So there's part A. Part B is just the graph you did on your calculator. Part C asks you, why at -1 and 0 the function is discontinuous. I think it's really easy to see why it's discontinuous at 0. We can't put zeros in to the bottom of a fraction, can we? And so I think you could just say f of x is undefined at 0 because I can't divide by 0. On the other hand, why can't you put -1 in? It's a little less obvious. Well, if I put a -1 in, I end up with in the parentheses 1 plus -1, which is 0, right? But this -1 up here says take the reciprocal of that, and the reciprocal of 0 becomes 1 over 0, which blows up into a vertical asymptote. So in both cases, you end up dividing by 0, which we know is not allowed. And so that's kind of the answer for part C. Part D says are either of the discontinuities removable? Well, the discontinuity at -1 is not, because as you can see in this graph, we're going to get a vertical asymptote, an infinite discontinuity that's not removable. The one at 0, the discontinuity at x equals 0, is a little harder to understand. What's happening right here? So here's some different pictures of what's going on. This slide right here is what's happening as we come into -1, and we see that vertical asymptote. So that one is an infinite discontinuity that can't be fixed. This guy is what's happening between -1 and 0, by the way. And I'll show you kind of a closer look at this one in just a second, so hang in there. And then this is what's happening on the other side of 0. And as we can see, the right limit as we approach 0 seems to be coming down to a height of 1. And you can zoom in on that and confirm that. And I've got a little table here that does kind of confirm that. I'm coming into 1, as you see, by 0.0001. So I'm getting closer and closer and closer to 0. And you can see these values really tightening up on the value of 1. So tabularly, that basically confirms that we definitely have a limit, right limit of 1. But what also it confirms is that it's just a single point of discontinuity, a hole. Okay, and so there it is right there, and that is removable. I could actually fix that by making a piecewise function, defining the height of the function at 0 to be equal to 1. So that one is removable. This, for some reason, this is kind of weird. This says that it wants me to say f of 0 is 0, but that's not right. It's got to be a height of 1. So go over that right there and fix it. All right. Now finally, part E says use the graphs and tables to evaluate what's happening as we move towards infinity. Well, it looks like as we move towards infinity that this line really flattens out. This is the graph from 0 to 5,000. Oops. And you can see that it comes up really steeply right here. It almost makes like a right angle turn almost, and then it just flattens out like crazy. where is it flattening out? That's really what we want to know. And this table shows us where it's flattening out at about 2.7, a little more than 2.7, 2.717, 2. Well, eventually we get up to 2.718. And so that's what the answer says here, is it looks like we are have a limit of about 2.718. But if we think about that value, it's really close to this number e that we're familiar with, right? And so here is the same graph going to 5,000, but I put in a horizontal line at E, because you have that button on your calculator, and you can see how you can barely tell them apart as you come through there. What I did was I zoomed in between 2.71 and 2.72 so that you could see our value of E, and that we have that horizontal asymptote that we're definitely approaching. And so this is the function that makes E, that derives E. The limit of this function as we approach plus or minus infinity. And you've actually seen this on a bonus previously. Here's if you plug E into your calculator, it tells you 2.71828. Okay. Here's the extra stuff I told you I'd show you. Between -1 and 0, we have that chaos. And what I did is I went by just 0.001s, and I started going back, and you can see that almost always it's undefined error, 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 error. Why is that happening? Well, because I'm doing 1 plus 1 divided by a tiny, tiny negative number, which is creating a really big negative number. So this whole thing in here is creating a really large negative number. But if x is any kind of an even root, because I'm taking it to a fractional value, right, less than 1, then it's impossible. Now, every once in a while, like here at -0.008, it creates a situation where the number inside and the number outside work to create a real number. So every once in a while, there's actually an answer, but only when you get values inside, which are, or I guess values outside, which are like perfect odd roots, like third roots, fifth roots, because then we can take those negative numbers and take the roots of them. But that doesn't happen very often, as you can see. So it's a really crazy graph that we get in there. But that's why it's like that. And then here, I just chased that horizontal asymptote to the right a little bit further. And you can see that, we got about 2.718, but then I went up to 9,000, and I got 2.71813. And I think if we went to 200,000, you would actually get all the way to 2.71828, which is accurate to 5 decimal places. So you can play around with that if you want. That was that problem. All right, so let's get down to the important problems. I think these are really important. Okay, and so I'm just going to do a handful of these to kind of show you the way that you want to write them. This problem, 25. The first thing we're going to do is we're going to factor it. Okay. And so we get different perfect squares on top, x minus 3, x plus 3, x plus 3 on the bottom, and you can see we really just end up with a reduced fraction of x minus 3. So here's how we define the function. This is the kind of problem you're going to see on the quiz. Your new function is your old function everywhere except where the removable discontinuity is. If there's a non-removable discontinuity, like an infinite discontinuity, there's nothing you can do to fix that, so don't worry about it. But on these, they tell you where the issue is. Most of the time on the quiz, it's not going to. All right, you're just going to have to know that only the holes that create the removable discontinuities can be fixed. So at -3, we've got an issue. So I need to plug that hole. And so at x equals 3, I need to find the height of the function to plug that hole. Remember, all the way back to Unit 1, when we did rational functions, when we were writing holes as ordered pairs, right? It should be -3, sorry. We would plug the negative, the x value, into the reduced equation. So we do -3 minus 3. That's how you figure out the height that you need to generate. So that would be the answer, and that should be the answer in your course pack for 25. You do the same thing, type of thing every single time. It's always going to be g of x equals the original function everywhere except where that x value of the removable discontinuity is, and then it's going to be the height of the removable discontinuity, the height of the hole, when x is equal to the x value of that removable discontinuity. This is always how it's going to look. Okay, so 26, we have a difference of cubes on top, so x minus 1, x squared plus x plus 1 over difference of squares, x minus 1, x plus 1. So g of x is going to be, we can see, the positive 1 is the removable one. There's a vertical asymptote created an infinite discontinuity at x equals -1, but there's not a darn thing we can do about that. So the original function, x cubed minus 1 over x squared minus 1, when x is not equal to 1, which is everywhere except for 1. Now, if x does happen to be equal to 1, what do we get? Well, let's plug a 1 in here. 1 squared plus 1 plus 1 divided by 1 plus 1, 3/2. That's your height. That's how you do these. It's, there's really not much more to it than that. 27 and 28 went back to the early problems we were doing a couple weeks ago when we had to know that relationship. This one is just the identity, immediately, the limit of sine of x over x as we approach 0 by identity, by the one that we establish is equal to 1. 28 I'll do because we have to think through it a little bit more, but not much. The problem with this guy is I need general form is kx over kx, and so 4x I have, but I do not have the kx on the bottom. I'm missing the 4 on the bottom. Some of you on that first quiz were trying to factor 4s out of signs. You can't do that, but I could add a 4 to the bottom. That was the trick. Now you can't add a 4 to the bottom unless you add 1 to the top, right? So then I could pull the constant 4 out of the top, leaving me with the limit as x goes to 0 of sine 4x over 4x. So that just became the 1 by identity that we were looking for. And so now we can say, all right, our new function g of x is going to be the original function sine 4x over x everywhere except for at 0. If x happens to be equal to 0, that height that we need to fill in to plug the hole is 4. Not 14, I accidentally put a little mark there, but ignore this, pretend it's not there. All right, 29 is totally different unless you happen to do the bonus problem on limits quiz 1 a couple weeks ago. And the trick here was to use good old conjugates. Now, some of you guys actually factored the top, which I guess you could do. X doesn't look like a perfect square, but you could call it root x times root x. So maybe you save yourself a step if you do that, root x minus 2, root x plus 2. But conjugates is the classic way of doing this. You do not factor the top. You'll see why in a second. First of all, it's a pain to do that. But second of all, you don't want to, because look at the bottom. The bottom is difference of squares. Root x times root x is x minus 4. So this guy cancels with that. Your reduced function is x minus 2. So that helps me to write this extended function now, because I know the original function is good to go everywhere except for, what was the issue with this right here? Wasn't it 4 that made a 0 in the bottom? Square root of 4 is 2 minus 2 is 0. So everywhere except for 4, I'm going to use the original function. But if x is equal to 4, what's that missing value? Well, now that I have my extended function, I can just say, oh, it's going to be at, this was supposed to be a plus because I need a plus on the bottom. Sorry about that. I can just do root 4x plus 2 or 2 plus 2. So that's a height of 4. And there you go. Okay. Now, the last one is the most interesting because the top doesn't look factorable. I mean, maybe you could use grouping, but then you look at that and you're like, there's no way I can group that. So how the heck am I going to do it? Well, they tell you where the removable discontinuity is. And so you actually know that you could use synthetic division with 2. But the more interesting question would be, what if they didn't tell you where the removable discontinuity was? It's not as bad as it seems, okay? Because the bottom factors into x minus 2, x plus 2. There's only 2 possibilities for the whole to be. There's only 2 possible, the negative 2 and 2 are either wholes or vertical asymptotes. If one of these divides into the top, then you're in good shape. And if it doesn't, then you can't do the problem. Okay, it's not going to have a removable discontinuity. So even if they didn't tell you which one to use specifically, just try one. And if it doesn't work, try the other one. I mean, there's only 2 ways to go. So let's say I tried the wrong one. Let's say I guessed negative 2. I always guess the positive one first because it's easier to divide out. And then if I'm wrong, I know it's got to be the other one. But here's synthetic division, right? We line up the coefficients going across, and then we add down, and then we multiply up, and then we add down, and we multiply up, and then we add down, and then we multiply up. And if it doesn't zero out, it's not evenly divisible. So this just told us right here that negative 2 is not a factor of the top. So then we're going to try positive 2, which this problem actually told us to use. But I just showed you how there's, you only have two options. And synthetic division is only going to take you a minute. So even if you're wrong, you only lose a minute. It's not a big deal, okay? So 1, negative 4, negative 11, 30. Let's try this one more time. 1 times 2 is 2. Negative 2 is when I add. Negative 4. Add negative 15. Multiply negative 30. Oh, look at that. Just like magic. So what I end up with here is x minus 2, right? That's the root I just did. And what's left over is x squared minus 2x minus 15. And that's where, that's what this tells you. Okay? So these guys cancel. That's the whole. That's the removable discontinuity. Some people like to factor this top if it works, and this one does. It would be x minus 5, x plus 3, but I tell you it's really not necessary. Your extended function g of x is going to be the original function everywhere except 2. At x equals 2, let's find out what it's going to be. We're going to take a 2, we're going to plug it in here, we're going to plug it in here, we're going to plug it in here, right? And I'm going to get 4 minus 4 minus 15 over 4. And what is that, negative 15 fourths? There's your answer, okay? So that's how you do those. Hopefully that helps more examples on how you do an extended function is what they call it. But really what it is it's just a function where a hole has been fixed by plugging it in. This is what this is. This is, there's a hole on our graph, and this is where we plugged the height of that hole. It's now been filled in, and it's no longer a discontinuity. That's really what's going on here. All right, we kind of talked about these a little bit, so hopefully that helped you out. You just have to interpret, if the limit does not exist, it's either got to be a jump or an infinite discontinuity. If the limit does exist, it's either got to be continuous or a whole, right? A removable discontinuity. So keep those in mind, because that will usually narrow it down to two things right away, if the limit exists or not. If you need more help on those, I can help you. There'll be, I think, one on the review you'll be working on. We did this one. Here's the one I want to talk about. So last one, okay? For this piecewise function, right? X squared minus 1 is a parabola. It's been shifted down 1 unit, so it kind of looks like this. 2ax, a is just a value, so 2ax is going to be just a line with a slope of 2a. Whatever a is, that'll tell us, multiplied by 2, that'll be the slope. So we have two different functions that are split at the value of 3. What we need to know, right, is what value of a has to occur so that these two functions meet at the same height. I need these. Oops, this guy was shifted down one, wasn't it? This guy needs to be meeting right there, right? What is this y value? And so it's just a little algebra problem. I know that 3 has to be the x value where this occurs, because it's the only breakpoint of these two continuous functions. So I'm going to go ahead and plug 3 into the top function. 3 squared minus 1, right? 3 squared minus 1 is 9 minus 1, which is 8. Okay, so I know that they have to meet at a height of 8. So now I just have to know where 2 times a times x is equal to 8. But remember, I know what x is. X has to be 3, right? X has to be 3. So I'm going to go ahead and plug a 3 in here. And now it's just a real simple algebra problem. 8 divided by 6 is 4/3. So if a is equal to 4/3, this line will have the perfect slope, so that at 3 they both meet. But if a is anything else, it'll have a different slope, and it'll have a different height at that value, and you'll get a jump discontinuity. So this is a really classic AP calculus question that you see a lot of times on their multiple choice tests. But that's it. So long solutions video. I wanted to talk a lot about these. So hopefully you just jumped around and listened to what you needed to. And feel free to let me know tomorrow if you have further questions. Okay. Good luck with your reviewing and your studying. And just make sure you reach out if you need anything else from me.